In this video, we're going to work the review exercises from Chapter 5. So Chapter 5 is on the normal distribution. So how we use the normal curve, the normal distribution, to make approximations about an unknown set of data. All right, so the first question says, the following list of test scores has an average of 50 and a standard deviation of 10. Use the normal approximation to estimate the number of scores within 1.25 standard deviations of the average. And so I've talked about this in the previous videos as we've gone through this chapter. It's a little confusing because we're using the normal distribution, the normal curve, to make estimates about a set of data. Right now, as a set of data, we're talking about a list of numbers, because the idea is if behind every histogram is just one list of numbers, a list of heights, a list of weights, it's one list of numbers. You can calculate the average of that list, the standard deviation. You can make a histogram. And so the histogram shows how the numbers are distributed. And if you can assume that that distribution is normally distributed or follows the normal curve, then you can use the normal curve to estimate how many data points are within, this interval of numbers. As they're talking about here, how many data points, estimate how many data points are within 1.25 standard deviations of the average. But this is a little confusing because we have the list right in front of us. We have the actual average, the actual standard deviation. So in practice, we wouldn't use the normal curve here. We would just make an actual histogram out of this list of numbers. But as I've mentioned, this is at this point in the course, in the textbook, we don't have the knowledge and the skills yet to actually talk about situations where we don't know the distribution. We don't know the data. We don't have the actual list of numbers for everyone in the United States, let's say. And so we need to assume that it's a normal distribution, and with that assumption, we can get estimates for how many of everyone in the United States, how many people weigh within this range, let's say. And you can imagine we won't even have for that entire data set, we won't even have the actual average or the actual standard deviation, because if we did, then we'd have the list of numbers. If you could calculate the literal average or the literal standard deviation, then you'd have the list of numbers. So just make a histogram out of that list and calculate the numbers that you want. You don't need to make any assumptions or approximations. But as I've mentioned, we're not going to worry about all of that right now in this chapter and these example problems about how we're actually going to make these assumptions, what we're going to use when we make an assumption for that something is distributed normally. What are we going to use for the average? What are we going to use for the standard deviation? Don't worry about all that. This is what we're doing here is purely for practice. We just want to understand the concept of the normal distribution, just illustrate the process of assuming something is normally distributed and how we go from there. All right, so this list of test scores here has an actual average of 50 and an actual standard deviation of 10. If we assume that the data here, this list of numbers here is normally distributed, okay, then we'll be making an estimate because this is most likely not perfectly normally distributed. Then let's use that normal approximation to estimate the number of scores, the number of these scores that are within 1.25 standard deviations of the average. Okay, so how do we do that? If we're assuming that this data follows the normal curve, then to estimate the number of scores that are within 1.25 standard deviations of the average, this is already in this 1.25, that's already in standard units. So within 1.25 standard deviations, we just need to calculate what's the area under the normal curve from minus 1.25 to 1.25. How do we calculate that area? Well, just like we've done in the previous videos, we're going to use the actual formula for the normal curve. I've input that formula into the graphing calculator, saved it as E. Okay, and just like we've done before, going to integrate from minus 1.25 to 1.25. We're already in standard units. Equation E with respect to X. And there it is, 79%. So approximately 79% of the data points, if we can assume this data is normally distributed, 79% of the data points are going to be within 1.25 standard deviations of the average. All right. Now, how many scores were really within 1.25 standard deviations of the average? Let's calculate the actual number. So, okay, 1.25 standard deviations. What is that? How much of a deviation is that from the average? What is 1.25 standard deviations? So 1.25 is 1 1/4. That's 5/4 times, so 1.25 times the standard deviation is 10. That's 25 halves, 12 1/2. Okay, so what is 1.25 standard deviations above the average? That's 50 plus 12 1/2. What about below? That's 37 1/2. All right, so let's circle all the numbers that are within this range. They're between 37 1/2 and 62 1/2. Okay, so there's 25 total values here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 are within 1 1/4 standard deviations. This is 0.72. So 72% were actually within 1.25 standard deviation. So that's not bad. The approximation was pretty good. You are looking at a computer printout of 100 test scores, which have been converted to standard units. The first 10 entries are these entries. Does the printout look reasonable, or is something wrong with the computer? All right, so these are in standard units. And when you think about standard units, that means that this value here was over 6 standard deviations below the average. This was over 6 standard deviations above. This was over 11 standard deviations below. Here's 7. So even if you look at this, there are 1, 2, 3, 4, even 5. You could say 5 values are it's saying we're more than 5 standard deviations away from the average. Now, it doesn't say, if it said that the test scores were that they were assumed that they were going to be normally distributed, then for sure there would be an error here. Because if you were assuming they're normally distributed, then we know that there should be very few scores that are like, if you're greater than 3 standard deviations away from the average in a normal distribution, then that's an outlier. Whereas we've got 5 that are 5 standard deviations away. But it doesn't say that this is normally distributed. Okay, so maybe there's some kind of distribution that is different than the way the normal distribution behaves. Right? You might be able to come up with a distribution that has a really long tail or something. And so you might have a group of data points that are really far from the average, unlike the normal distribution. However, that rule that we learned for the normal distribution, that's 68%, 95%, in general, that's not wrong. Like, you're not going to expect to see that many data points, and no matter what the distribution is, that are farther than 3 standard deviations away. It's not like that's like, you can't violate that too much, because then you're violating the meaning of standard deviation, the meaning of average, right? If you've got data points that are far away from the average, then the standard deviation is going to go up to compensate for that. You're theoretically, you're never going to have too many points that are that many standard deviations away from the average, because then the standard deviation would have just been higher. And so there's something wrong with the computer, I would say here. If there was just a little bit of a deviation from the pattern that we're familiar with normal distribution, that 68%, 95% rule, if it deviated a little bit from that, then you might say, well, hey, it's just, maybe it's not a normal distribution. But if it deviates like a lot like this significantly, then there's something off. From the mid-1960s to the early 1990s, there was a slow but steady decline in SAT scores. For example, take the verbal SAT. The average in 1967 was about 543. By 1994, the average was down to about 499. However, the standard deviation stayed close to 110. The drop in averages has a large effect on the tails of the distribution. estimate the percentage of students scoring over 700 in 1967. Estimate the percentage of students scoring over 700 in 1994. You may assume that the histograms follow the normal curve. Okay, so the first thing I've noticed here is it's saying that the average in 1967 was about 543. Then by 1994, it dropped to about 499, but the standard deviation didn't really change. And so I think about what we learned in the change of scale in the previous section, how if you have a histogram and you change just its average, but it's not its standard deviation, that's like equivalent to adding or subtracting a constant from every data point in the list. And so this is a little different than that concept, because when we're comparing the SAT scores from 1967, we're not making adding or subtracting a constant to that exact same histogram. So the scores are going to be different. You're going to have totally different scores in 1994. But I think we can look at it that way. Just in a general sense, we can kind of look at it that way, that it was just a general steady decline in SAT scores. Just the average score dropped. It was the same. The deviation didn't change. And so if you compared all the SAT scores in 1967 to those in 1994, if you could, in a sense, break it down to just subtracting a constant from everyone's score, it's not going to, it won't look that way. It won't be that won't be the case, but kind of on average, that's what happened. If you're going to make the statement that all that happened over the course of this 30 years was that the average score dropped, then in general, what you're saying is that in general, every student's score just went down by about 50 points in general. And you can make that statement because what they're saying is, look, the average dropped by 50 points but the standard deviation didn't change. So it's just the scores have dropped, right? Students in general just aren't scoring as well. So it's like, in effect, this is not literally what's happening, but in effect, it's kind of like every student's score is just going down by 50 points. You take the valedictorian from 1967 and compare it to the valedictorian in 1994, the score has dropped by 50 points. That's not literally what's happening, right? You might have a student that in 1994 is a genius and smarter than any student ever in 1967, but on average, that's what's happening. On average. All right, so if we're assuming, though, we can assume that both the distributions of these scores in 67 and 94, they're both normal distributions. And so all it is just from 1967, here's 1967, and then to 1994, it's just shifted to the left. The average has shifted, and that's it. How can we estimate the percentage of students scoring over 700 in each of these years? Well, we just need to convert 700 to standard units. So, okay, let's do this in 1967. The standard deviation is the same in both years. How many standard deviations? Well, okay, but in 1967, how far above the average is 700? 157. Now, how many standard deviations is that? Okay, so this is 1.43 standard deviations above the average. Okay, what about 1994? The standard deviation is the same, but the distance from the average is going to be different. 700 is, we're comparing this to 499. So how many standard deviations is that? 1.83. Okay, so what percentage of students scored over 700 in 1967? Well, what percentile is this? And then we'll take 100 minus the percentile, right? So what percentage of students scored lower than 700 in 1967? Well, we're not going to do that, but just pointing that out. You could think about it that way. If you find out what percentile this 700 was in 1967, then just take 100 minus that. And same thing here, but we're going to go ahead and just do this. So scored over 700, we would take So we want to solve for, we're going to infinity. The limits are, upper limit is infinity. The lower limit is, we don't know. Or no, we do know. Yeah, it's 1.43. Yeah. So 7.6%. Okay, so this is 7.6% scored over 700 in 1967. What about in 1994? Same thing, it's just now the z-score is different. 3.4%. Okay. SAT scores range from 200 to 800. It does not seem that the SAT was getting harder. Most of the decline in the 1960s is thought to result from changes in population of students taking the test. The decline in the 1970s cannot be explained that way. From 1994 to 2005, scores generally increased. The test was renormalized in 1996, which complicates the interpretation. The averages mentioned above were converted to the new scale. All right, so most of the decline in the 1960s is the result from changing the population of students taking the test. I'm not sure what they mean by that, because why would what does the population have to do with what the average score is? Are you bringing in students that, are they suggesting that the increase in the changes, the population changes, where you had more, I guess, students that would get lower scores coming in? Is that what they're saying? The decline in the 1970s cannot be explained that way. From 94 to 2005, scores generally increased. The test was renormalized in 1996, which complicates the interpretation. The averages mentioned above were converted. I don't know what renormalized means, so I'm not sure what they're saying here. On the math SAT, men have a distinct edge. In 2005, for instance, the men averaged about 538 and the women averaged about 504. Hell yeah, that's right. Just joking. Estimate the percentage of men getting over 700 on this test in 2005. All right, so we're assuming it's normally distributed. Yeah, you may assume that histograms follow the normal curve. Wait, what is this about? Assume 1. Yeah. Okay, so we can assume that these histograms follow the normal curve and that both standard deviations were about 120. We've got the averages of both histograms. So the percentage of men getting over 700 on the test in 2005. Well, what is 700 in standard units? So if the standard deviation is 120, so how far above the average is 700? 700 minus 538, we're talking about the male histogram, and then standard, and how many standard deviations is that? It's 120. So Z is equal to 1.35. Okay. Women getting over 700 on the test in 05. Let's do the same thing. So 700, and how far above the average is that? The women's histogram was 504, same standard deviation, 1.63. Okay, getting above is what they're saying. Getting over 700. Okay, so now we just come back here and we go from we put in the formula for the normal curve. We've done this in the previous videos many times. And there's the lower limit, there's the upper limit, because we want the area above this score. So 8.9%. All right, and then this is 1.63. 5.2%. All right, now why is this percentage lower? Because if you scored a 700 on the women's test, you did better than, the average was lower than the men's test. So your percentile is better. In Haynes 5, so we talked about Haynes 5 in chapter 4. This is just, they did this was in 2004-ish, they surveyed 3,000 men or women and just asked them health and nutrition questions. Their age, weight, height, blood pressure, things like that. The men aged 18 and over had an average height of 69 inches and a standard deviation of 3 inches. The histogram is shown below with a normal curve. So you can assume that if you didn't have the actual distribution, you could assume it's normally distributed. But you do have the actual distribution, so why would you even assume a normal curve? This is just for illustration. The percentage of men with heights between 66 and 72 inches is exactly equal to the area between what? Exactly. So not an approximation. The area between 66 and 72 inches under the histogram. 66 inches and 72 inches under the histogram. And that's why if you actually had the numbers, the literal numbers, you wouldn't use any normal approximation. You just get the exact answer. This percentage is approximately equal to the area between. So the approximation, if you didn't have the actual histogram, you could use a normal approximation, and that would be between. And so I'm assuming that the only options are -1 and 1. So I'm assuming this must equal, if the average is 69, and then 4 inches above, or no, okay. The average height is 69, standard deviation is 3 inches. Oh, this is 72, yeah. 3 inches above and below, one standard deviation is 3 inches. So -1 and 1, under the normal curve, you convert to standard units, and yeah. You convert to standard units and calculate the area under the normal curve. Among applicants to one law school, the average LSAT score was about 169. The standard deviation was about 9. And the highest score was 178. Do the LSAT scores follow the normal curve? Okay, this is interesting. Among the applicants to one law school, the average LSAT score was about 169. The standard deviation was about 9, and the highest score was 178. With that information, do we have enough to say with some confidence that the LSAT scores in general follow the normal curve? To me, I'm going to say my first instinct is no, but let's take a look. The average was 169, standard deviation was 9. The highest score was 178. So what's 178 minus 69? Minus 169. That's 9 plus 9. That's 1 standard deviation away from the average. Well, okay, I wasn't expecting that. I thought that they were going to say that, I thought 178 was going to be like 5 standard deviations away, let's say, from the average, or 4 or 3. And let's say that was the case. Let's say 178 was like 4 standard deviations away from the average. Well, most of the data points for a normal distribution are within 1 standard deviation, and there's barely any within that are farther than 2 or 3 standard deviations, or farther than 3 standard deviations. But this is just one score, and it's the highest score. So you can have a normal distribution and have 1 or maybe 2 points that are far, far away from the average. It's just if you start seeing multiple points, then it doesn't make sense. So in that case, it would be inconclusive. Yeah, because you might be tempted, if this was 5 standard deviations away from the average, you might be tempted to say, well, that means that it's not a normal curve. No, it's inconclusive. It could be, it couldn't be. It might be, it might not be. You don't know. You need some other scores. Now, in this case, though, this is a little different, because the highest score is plus 9, and that's within 1 standard deviation. So that's suggesting that, okay, what do we know about the normal curve? Well, one thing is that it's symmetric. Okay, so if this followed a normal distribution to some extent, then if all of the scores on the high side of the average are within 1 standard deviation, which that's the case here, because this is the highest score. Then in general, all of the scores on the lower end are going to be within 1 standard deviation as well. Well, that's not a normal distribution. So the answer here is going to be actually no. Not no because it's inconclusive. We can't say if it is or isn't. No, we could say it's not. Because a normal distribution, it's 68% of the data points are going to be within one standard deviation. So it doesn't mean that if you find a distribution that, oh, it's 71%, then it's not a normal distribution. No, it just, in general, it's going to be like that. So if we could conclude that, well, there's about 75% of the data points that are within one standard deviation, okay, you could say that potentially follows a normal curve. Maybe even 80% if you're stretching it a little bit. Maybe 80%, 81%. That's stretching it a little bit, but you see what I'm saying? But not 100%. That's way away from 68%. And that's violating, not only is it way away from 68%, it's also violating that with a normal curve, about 95% are within two standard deviations, which means that 32% are in the range from 1 to 2 standard deviations. Here, 0% are in the range from 1 to 2 standard deviations. So the answer is no. These LSAT scores did not follow the normal curve. Okay, we're going to work the remaining 6 problems in the next video.